Welcome back to Algorithmic Game Theory. Over the past lectures, we've got to know truthful mechanisms, more precisely dominant strategy incentive compatible mechanisms. These had the property that players or bidders always want to report their true values regardless of what the other players are doing. It is a dominant strategy for them to do so. But we've also seen that sometimes this doesn't work. Sometimes it's not possible to design a simple, truthful mechanism. And why is it that we're insisting on this truthfulness anyway? How can we understand non-truthful mechanisms? This is exactly the kind of question that we want to start answering today. But how would we analyze such a non-truthful mechanism? Because we still want to take into consideration that players will behave strategically. So if it is not in their best interest to report their true value, then they might lie. One thing that we might want to do is we might just consider pure or mixed Nash equilibria of the resulting game. However, there's one big weakness about this, because for a pure or mixed Nash equilibrium, what you will always be considering is the case that actually all players know each other's values. Why that? Because to find this equilibrium, you would then all of the players have to know what the other players' utilities are like, and the utilities depend on these private valuations. And this makes this a little weak. So we might now argue, for example, for a first price auction, that if a pure Nash equilibrium exists, it will always be great. But how should the agents ever end up in such a pure Nash equilibrium? Because what they are choosing there as their strategies depends on what the other players have as their values. And this is exactly private information. So today we'll get to know an equilibrium concept which works with incomplete information. So also now the players don't know the true values of the other players, but they do have a belief about this. And this is called a Bayes-Nash equilibrium. Let's see how this is defined. We'll assume that bidder i's value Vi out of capital Vi is drawn independently from some distribution Di. These distributions are known to all bidders. And now, each player or each bidder, however you want to call these here, each bidder will now choose a bid Bi. Of course, this bidder knows his or her own value, but not B minus I. Only the distributions that B minus I is drawn from. How can we capture this? We can now say, in other words, that each bidder chooses a bidding function which we call beta I, which maps from the set of all possible values to bids. And we now say that whenever the value is Vi, bidder I bids beta I of Vi. For example, truthful bidding will be just the function that beta I of Vi is equal to Vi. And now we say that such a choice of a bidding function for each player is a Bayes-Nash equilibrium if no player can benefit from unilaterally choosing a different bidding function. So, in a way, we can understand this now as a game of choosing the bidding functions. The strategies are now the bidding functions, and we are kind of interested in a pure Nash equilibrium of this game of bidding functions. More formally, this looks as follows. A pure Bayes-Nash equilibrium or for short BNE is a profile of bidding functions beta I for every player that we have. The beta I is mapping from the possible valuation functions of bidder I to his or her possible bids. And now we'll have to define the equilibrium condition for all players, all possible values, and all possible deviation bids. The following holds. Take the expectation of Ui of beta of V, Vi, and this will be at least the expectation of Ui of Vi prime, beta minus I of V, Vi. And here we mean that beta of V is just the vector of beta 1 of V1 up to beta n of Vn. Okay, let's digest this definition. A Bayes-Nash equilibrium, what is this now? This is now one choice of a bidding function for each of the players. So each of the players chooses now such a bidding function. And this now has the property that no player wants to deviate unilaterally from this bidding function. And you can state this in two different ways. Before I was stating this by saying, okay, you don't want to choose a different bidding function than the one that you're choosing, but you can also say it like this, and maybe this is even more intuitive. So you are player I. You now consider one of your possible values, small vi, out of capital Vi. And now you ask yourself, do I want to bid beta I of Vi or something else? Something else, this is Bi prime. Now, what do I know about the other players? I don't know their values, so I don't know their bids. But I know the distributions their values are drawn from. So I'm taking into consideration the expectation that I'm getting if now each of the other bidders is drawing one of their values from the distribution, and then they are bidding according to beta. And what we see here is that everybody's bidding according to beta. So we'll draw all V's except for Vi from the distribution. And then we're asking, what's my expected utility? This is what is happening here. Vi, that is fixed. The others we draw from the distribution. Here it is very convenient for us that those are independent. So the other bidders' values are independent of my own value. Otherwise, things would get more complicated. So this is what we see here, and what do we see here on that other side? Here we see, again, the other players don't change. They still draw their values from the distributions, and they play according to the beta I functions, beta I prime functions. But we are now bidding Bi prime instead. And does this now make an improvement for us? Do we now get a higher value by bidding Bi prime rather than beta I of Vi? What this bidding function would be doing, would be proposing. If so, then this is not an equilibrium. But if not, then it is an equilibrium. Let's see one very simple example. In a truthful mechanism, and by truthful I mean dominant strategy incentive compatible, to be precise, we have definitely one pure Bayes-Nash equilibrium, namely truthful bidding. It is not necessarily the only Bayes-Nash equilibrium, but it is always a Bayes-Nash equilibrium. Why that? Because this term here is maximized, or rather let's talk about this term here, for which bi prime is this inside the expectation maximized for a truthful mechanism, it is always maximized for bi prime equal to vi, regardless of what the other players are doing. Truthful bidding is a dominant strategy. And this is exactly then sufficient for this inequality to hold, because even if all the other players are bidding truthfully and we take the expectation over the other players, even then it will not be better to do something else. Good. But maybe this is not enlightening enough. Let's consider a first price auction, which is not a truthful mechanism, but for which we can also derive a Bayes-Nash equilibrium. Let's consider a first price auction with two players. And let di for both players be the uniform distribution on the interval 0 to 1. And what we now want to show is that beta I, the vector of beta I, where beta I of vi is equal to a half times vi, that this is a Bayes-Nash equilibrium. Okay, before we go into the details, what is it that we're claiming? We are now considering a first price auction, and now we have two players, and we are now in a setting where we assume that these variations are drawn from distributions, are drawn from known distributions. These distributions are known to everybody, so these are prior beliefs on what you assume that these values are. And everybody agrees on these. In this case, we say, okay, they are drawn from the uniform distribution on the interval between 0 and 1. And we now claim that always bidding half your value, this will be a Bayes-Nash equilibrium. Bidding your true value, this will usually not be an equilibrium, as we've seen, because this gives you always zero utility. But it seems that bidding half your value, this is a reasonably good choice. How so? Let's only consider bidder 1. For symmetry reasons, it's really enough to consider only bidder 1, because for bidder 2, the situation is exactly the same. And let's now fix any value for him or her. What will now be the expected utility when bidding some bi prime against now beta 2. So the other player is playing according to what we now claim is the Bayes-Nash equilibrium. Let's write this down. The expected value we are now drawing V2 from D2, and now we take the utility of player 1 when player 1 is bidding B1 prime. Player 2 is bidding according to beta 2, so they're bidding beta 2 of V2, and the value of beta 1 is V1, something that we fixed. What will this be like? Well, let's take this expectation, let's write this out. And in this case, writing down the expectation is pretty easy. Because we just have to take the integral from 0 to 1. Because we're considering the uniform distribution here. And now let's plug in the choice of beta 2. This is equal to V2 over 2. Now, how big is this thing that we're integrating over here? How big is this? This now depends on how much we're bidding. We can either bid more than V over 2 or we can bid less than V over 2. If we're bidding more than V2 over 2, then we're getting our value minus our payment. Our payment will be B1 prime. So this happens if B1 prime is bigger than V2 over 2. And otherwise, we're not getting the item and we're not paying anything. So we're getting 0. Good. So this now lets us rewrite this integral because we now have to just see that from 0 to 2 times B1 prime, we are getting V1 minus B1 prime. We're still integrating over V2 here. So this was just, I could mention quickly that this is equivalent to V2 being less than 2 times B1 prime. Plus, now for the remainder, we are getting 0. And this is, by the way, only true if B1 prime is at most a half. So in this case, if we now solve this, then we're getting V1 squared over 2 minus 2 times B1 prime minus V1 over 2 squared. So for which B1 prime is this maximized? This doesn't depend on B1 prime. And then we're subtracting something that is non-negative. And if we now set B1 prime to V1 over 2, then we're subtracting exactly 0. For any other B1 prime, we're subtracting something that is greater than 0. So we see that this is maximized for v1 prime equal to v1 over 2. And this tells us that the expectation of u1 of v1 over 2, comma, beta 2 of v2, comma, v1, this will always be at least what we're getting for any other possible bit b1 prime. This is true for all v1 and for all b1 prime. And this exactly means that this is a Bayes-Nash equilibrium, because this was exactly the equilibrium condition for player 1. For player 2, we get the exact same calculation because this setting is entirely symmetric. So for one particular distribution over the variations, we were now able to indeed derive a Bayes-Nash equilibrium, or we didn't actually even derive it right now. I just told you this is an equilibrium and then we verified that it was. But how would we in general solve for an equilibrium? How could we in general figure out what an equilibrium would be like? This is what we'll be doing next. So now we know the definition of a Bayes-Nash equilibrium. We've already seen 2 examples, but these examples were just the way that I told them that this is a Bayes-Nash equilibrium, and then you were able to verify that it actually is. How would you figure out a Bayes-Nash equilibrium yourselves? Let's do this for first price auctions, but only for the case that the distributions are identical. So all players are have their values drawn from the same distribution, and also we assume that the equilibrium is symmetric. What we'll do now is we'll derive a sequence of necessary conditions so that we then end up with some formula, and then one can actually verify that this is indeed a Bayes-Nash equilibrium. Which we will not do then, because this looks exactly the way like what we've just done, verifying that some bidding functions are actually a Bayes-Nash equilibrium for a first price auction. What is it that we're assuming now? We'll assume that for all players I and all x, which are non-negative, the probability that the value beta I is at most x, this is exactly equal to f of x, so this was our notation. But we'll also assume that this is a continuous distribution, which means that there is a density function small f of t, so that the probability that we see a value of at most x, this is exactly equal to the integral from 0 to x small f of t dt. further, we assume that we are in a Bayes-Nash equilibrium. So there is a Bayes-Nash equilibrium beta I, where I is an n, for which all functions are identical and invertible. Maybe this is too much to ask for, then one would probably get a contradiction somewhere, but as we will see, this does work out. So we will be able now to derive what these functions beta I will look like. To this end, let's also write, I forgot this before, we'll also write g of x for f of x to the power of n minus 1. This will be useful just as a shorthand later. What do we now have to have in this for these functions beta I to be a Bayes-Nash equilibrium? For these to be a Bayes-Nash equilibrium, we again have to have that the equilibrium property is fulfilled, which means that no bidder wants to deviate from what the bidding function is telling them and this should be true for no vi that they can have, for no possible value. Let's write this down. For all I, vi, and y, we now have that the expectation of the utility when we bid y, I mean now player I, the others bid according to beta, our value is vi. And we're taking, of course, the expectation over the other players. How big is this? Well, we know that this is a first price auction. So our utility will be vi minus y times the probability that no one bids more, or in other words, that for all j which are not equal to I, beta j of vj is less than y. By the way, there is always the question of tie breaking when you talk about these auctions, but here it really doesn't matter, because the probability that anything is equal to y, for example, that is 0 anyway. So this is something we can totally ignore for today, fortunately. Good. What is now this probability? This probability is we always apply function beta j on vj, and then we ask, is this less than y? What do we know about that? We know that these vj are independent. And this is something we've already used here, this is something that is somewhat implicit, that everything so what the other players' values are, this is independent of vi, But moreover, their values are also independent. So this probability is equal to the product of the individual probabilities. And let now phi denote the inverse of beta j, or beta I for that matter. We assume that those are all these bidding functions are identical. Then this will be equal to vi minus y times the product of all probabilities that Vj is less than phi of y. And the probability that Vj is less than phi of y, that's something we can also write down, because that's simply f of phi of y. And we're now having here the product of n minus 1 terms, so we have a shorthand notation for this. This is simply g of phi of y, because we said g is just f to the power of n minus 1. And here we're using a lot that all these distributions are identical, and also that these functions are identical, because otherwise this wouldn't be true. And also if they weren't identical, this would be a lot harder. But that's fortunately something we are not having to deal with today. We are keeping things simple. Good. Where are we now? We've now written down for any player, any value that this player might have, and anything that player might bid with this value, what will his or her expected utility be like? This will be exactly this thing. This will be exactly equal to vi minus y, so value minus bid, times g of phi of y. And why are we doing this? Because now beta I of vi has to maximize this. And this now helps us to derive what this beta I will have to look like, because also phi is the inverse of beta I. More precisely, if beta I of vi is equal to y, then, and here this is obviously an assumption that I forgot to mention, we also assume that these beta functions are differentiable. And I have to apologize at this point that all of this looks a little hand-wavy, and people complained to me about this in the past, that this looks a little hand-wavy, and yes, I agree. This is somehow more the way economists like to do things, maybe less worrying about are these things even differentiable or not, and rather deriving insights from this. So this is always just like between mathematicians and physicists, you always see the conflict of either of finding out real things or doing things very formally. Good. So my point was, this function is maximized for beta I of vi being equal to y. So let me rather state it, it is maximized for y being beta I of vi, which means that for this, the derivative by y has to be 0. What's this derivative? We'll have minus g of phi of y plus vi minus y times the derivative of g times the derivative of phi. What is now the derivative of this phi? The derivative of phi, what was phi? Phi was the inverse of beta. So we get this, the inverse of it, via the inverse function theorem. So the inverse function theorem tells us that phi prime of y is equal to 1 over beta I prime of phi of y. So what do we get? We'll get that minus g of phi of y plus vi minus y times g prime of phi of y times 1 over beta I prime of phi of y. This will be 0. Good. Now we replace y. What was y? Y was the bit that we wanted to have. What we now said this holds for the bit that we should choose when our value is vi. So let's replace every y by beta I of vi. And phi was the inverse of beta I. So phi of beta I of vi is equal to vi. So all of this combined now gives us that minus g of vi plus vi minus beta I of vi times g prime of vi times 1 over beta I prime of vi. This will be 0. Or equivalently, we can say that beta I prime of Vi times G of Vi plus beta I of Vi times G prime of Vi. This will have to be equal to Vi times G prime of Vi. What do we see on the left-hand side? On the left-hand side, we see the product of the derivative of beta I and G. So we will have to have that beta I times Vi times G of Vi, this will be the integral of Vi times G prime of Vi dVi plus some constant. And finally, as beta I of 0 has to be equal to 0, we now see that this constant has to be 0. So beta I of Vi will be equal to 1 over G of Vi times the integral from 0 to Vi t G prime of t dt. And now you can verify that this is indeed always a Bayes-Nash equilibrium. I don't always like these calculations because I think they are a bit sloppy mathematically. They feel like some heuristic approach, but eventually it doesn't matter how you derive down here. What you see is, okay, you can actually go through all these steps, and they just tell you which way to look for a Bayes-Nash equilibrium. And then you end up with this equation here, and then what you can do is you can actually verify that this is a Bayes-Nash equilibrium. How would you verify that this is a Bayes-Nash equilibrium? You would simply do what we were doing before for the first price auction, but more generally, namely plugging in this beta I function and then asking, what if everybody behaves like this? Do you want to deviate or don't you want to deviate? And the thing is, for every Vi following exactly this beta I function, when everybody else is doing as well, in expectation, this will be a good idea. And this is exactly what makes this a Bayes-Nash equilibrium. Of course, this does not show that there is no other Bayes-Nash equilibrium, and that's indeed an interesting question. Are there other Bayes-Nash equilibria? Well, one thing that's for sure is that there is no other Bayes-Nash equilibrium which is symmetric and for which the bidding functions are invertible and differentiable, because if this is the case, then our calculations lead to the point that, okay, the function beta I has to look this way. But at the same time, there might be points which just you will never see at all. And for these, it maybe doesn't matter what you're bidding. So there are many mathematical subtleties in here, but this is not the point which I want to discuss today. I just want you to get an understanding of Bayes-Nash equilibria and how you can generally derive necessary formulas for Bayes-Nash equilibria. But fortunately, to derive an understanding of what a Bayes-Nash equilibrium is like, you often don't really have to solve for the exact Bayes-Nash equilibrium, but you rather can argue about properties that the equilibrium is fulfilling. And this is exactly what we'll do next. So far we were asking the question, how do bidders bid in a Bayes-Nash equilibrium of a first price auction? But actually, that's maybe not even the thing that we're interested in, but rather we're interested in the question, what's the welfare of what they are doing? Is the one who has the highest value, is he or she always getting the item? Or can it happen that sometimes somebody who has a smaller than the highest value is getting the item just due to this overall strategic behavior? And this is exactly the question that we want to answer now. So we would now want to discuss the question, what is the welfare, the expected welfare of a first price auction in a Bayes-Nash equilibrium? For the symmetric case, so where the distributions are symmetric, are identical, and also the bidding functions are identical, we already have derived a formula for the exact equilibrium. And if we have a closer look, then we see those are increasing functions. And this means, who wins the auction? The one with the highest bid. But who has the highest bid? Because they are all using the same bidding functions and they are increasing, the one with the highest bid also has the highest value. But generally, this is not the case. Let's first write down this observation. In the symmetric Bayes-Nash equilibria, beta I of a first price auction with identical distributions for all V will have that the sum of the Vi of F of beta of V is a very contrived way of writing what's the value of the one who wins the item is exactly equal to the maximum value. I'm writing this in this complicated way because this is the way we'll also see this later happening in a more general way. So once again, what is it that we see? We have any valuation profile V. Now, everybody bids according to the Bayes-Nash equilibrium. Then we ask who wins the auction. This is the F function. Again, F, that's the outcome rule of the mechanism. And then we ask what's the value for this outcome. And we see, okay, this is exactly equal to the maximum value of that bidder. of all bidders. But this is not always the case. For example, we might have V1 being uniformly distributed on the interval 0 to 4/3, and V2 being uniformly distributed on 0 to 4/5. Then the bidding functions will look like this. So here we see Vi plotted against beta I of Vi. And there's now this player 1 who will have values between 0 and 4/3, so somewhere in here. And there's the other player who has values between 0 and 4/5. And what's now the point? The point is that sometimes it can happen that the bidder with the smallest value, with the smaller of the two values, wins. Namely, this happens if the blue bidder, so bidder 2, is inside this interval here, and the red bidder is inside this interval here. Then, as we're seeing here, beta on this point is higher than beta 2 on this point here is higher than beta 1 on that point. And so this means that not always the bidder with the highest bid will win. This means that the social welfare might not be optimal in the sense that, okay, always the bidder with the highest value wins the item in every Bayes-Nash equilibrium. Nonetheless, we are able now to still derive a guarantee for any Bayes-Nash equilibrium of a first price auction, regardless of the valuation distributions. And so the statement is that in any Bayes-Nash equilibrium, beta I of a first price auction the expected welfare that we see, so take the expectation drawn over all valuation profiles V, and now take Vi of F of beta of V. This will be at least half the expected maximum of the Vi. So what does this theorem tell us? Let's have a short closer look. It tells us that the expected welfare, when we're now drawing some valuation profile V from the distributions, and all players play according to the Bayes-Nash equilibrium, whatever this Bayes-Nash equilibrium is like, we don't actually care, it is any Bayes-Nash equilibrium. Then what's the expected social welfare that we're seeing? This will be at least half the expected maximum social welfare. The maximum social welfare, always point-wise, is the maximum value. And we're comparing this now also to the expectation of this. And I hope you see that this looks a bit similar to these price of anarchy statements, where we are also saying, okay, maybe it's not socially optimal what's happening in an equilibrium, but we are able to bound the ratio. We are able to say, okay, the expected social welfare is at least this fraction of the expected optimal social welfare. How do we prove such a statement? One thing that you might be tempted to do is to now try to figure out what the exact equilibrium is like. And I promise you, you'll fail because this is horribly complicated. What we'll do instead is we'll simply rely on the properties of the Bayes-Nash equilibrium, like we also did this in the price of anarchy analysis back for not only pure Nash equilibria, but then we also extended this, for example, to correlated equilibria. And in a similar way, we will be doing exactly like this, like now. So maybe let's start with just the case that we have a pure Nash equilibrium rather than a Bayes-Nash equilibrium. What would that even mean? That's just the special case that these distributions just have a point mass, that you always have one particular value for sure. Then a Bayes-Nash equilibrium corresponds to a pure Nash equilibrium. Let's see what will happen then. So we also call this in the full information setting. This means that di is deterministic, so it is a point mass, however you want to call this. And then we'll have a Bayes-Nash equilibrium is now a pure Nash equilibrium. So the bid vector and the valuation vector are fixed. And then this is truly easy, because how would you do that? What's the social welfare of Vi, of F, of B? This is exactly equal to the sum of the utilities plus the sum of the payments. And now we let I star be a bidder of maximum value. And what would now happen if this bidder was bidding half his value or her value? So if I now bid half my value, what will my utility be? The utility of this bidder will be Well, either I now win the item, which means my value is vi star, my utility is vi star minus bi star prime. This should have a star too. Or it is 0 otherwise. And the amazing thing is we can say, okay, this will always be at least the value, this will always be at least half the value minus the highest of the other bits. Why that? Because either a half times vi star is less than the maximum bit, in which case this is something negative, but then we're in the bottom case here. Or a half times vi star is more than the maximum of the other bits, then we're in this first case and the bidder wins. And then what is important here is that then bi star prime, this is exactly equal to a half times vi star. Good. So, what does this tell us? We are again in the first price auction, and we're just figuring out what a bidder of highest value could do. A bidder of maximum value could just bid half his or her value, and then that bidder would get at least this utility. Now the point is, that we are in an equilibrium, so you wouldn't benefit from deviating to this choice. Which means now the following. We'll have that ui star of b comma vi star. This will, of course, still be ui star of bi star prime comma b minus r star comma vi, missed the star up there. And so we have this inequality. And for all other bidders, we now have that the value they are getting should be at least 0. The utility that they're getting is at least 0. So, what we're getting is that the utility summed over all bidders will be at least a half times vi star minus the maximum of all bids other than I star, and this is at least a half times vi star minus the maximum of all bids bi. And what does this mean for our social welfare? Our social welfare will be the sum of the utilities plus the sum of the payments. This will be at least a half times vi star minus the maximum bid And what's the sum of the payments? The sum of the payments is exactly the maximum bid. So this will be a half times VI star. Cool. So this maybe looks a little weird when you're doing this for a pure Nash equilibrium, because a pure Nash equilibrium for a first price auction, that's actually, you would be able to say much more explicitly what is happening there. But we are not saying, okay, we don't actually care what the equilibrium looks like. We just say, okay, just if the one who has the highest value bid half their value, the others don't bid anything, then nobody is gaining from these deviations. So we'll have that the sum of the utilities is at least something, and then in combination we get that this is at least half the optimal welfare. And now the amazing thing is we can do the exact same thing also for Bayes-Nash equilibria. And it will not be any different. So the proof for Bayes-Nash equilibria will now look as follows. What is the expected utility when everybody's bidding according to the Bayes-Nash equilibrium? Well, suddenly it is not beneficial for me to unilaterally deviate to bidding half my value. This holds for all I and all VI. So in particular, we can also take the expectation over VI, because this holds for all VI. And then we get something that looks almost the same, except for that we now take the expectation not only over V minus I, but over all V. And bilinearity of expectation we now get that the expected sum of the utilities in equilibrium will be equal to the sum of the expectations and this will be equal, this will be at least when each player now unilaterally deviates to half their value. And now we can use linearity of expectation again. So nothing really happening here except for that we may do this inside or outside the expectation. This might look familiar because we were doing similar things when we were bounding the price of anarchy for correlated equilibria and coarse correlated equilibria. Good. Now we already know something, namely we have a lower bound for the expected sum of utilities in equilibrium. Now we do the exact same things that we were doing before, namely, for every fixed V, the utility of Vi over 2 comma beta minus I of V comma Vi, this will be at least Vi over 2 minus the maximum of the other bits. And also, the utility will also be non-negative, because if I bid half my value, then in a first price auction I'll never have negative utility. So if we now combine this, then we get that the sum of the utilities, if everybody now deviates unilaterally to half their value, this will be at least the maximum of all Vi over 2 minus the maximum of all beta I prime of Vi prime. Why that? Because for all but one of the players who has the maximum value, we can use this bound, and for the other, we can use that bound. And now, the one thing that we still have to observe is that the maximum of these will be equal, the maximum bid is equal to the sum of the payments under the same bid profile. And so, what we're getting is that the sum of the utilities will be at least plus, and by that I mean the sum of the utilities after each player unilaterally deviated, plus the sum of the payments. That together will be at least the maximum of all Vi over 2. And then I claim we're done, because we now say, okay, the expected social welfare at equilibrium. This is the expected sum of utilities plus payments at equilibrium. The sum of the expected sum of the utilities is at least the expectation of this. And the expectation of that other term, this is exactly, well, as I was saying, the expected sum of the payments. So bilinearity of expectation, then the rest follows immediately. So if this was too fast for you, you're probably not the only one, but don't worry, because this is a proof template that we'll see again. Maybe let's once again go through the idea of the argument. We want to now say, we first of all say that the expected social welfare is the sum of the expected sum of the utilities, and for the expected sum of the utilities, we can say this is at least the expected sum of the utilities after each player unilaterally deviated to something. And then we say, okay, what is now this sum here? The sum of the utilities if players unilaterally deviate. For this, we derive a lower bound. And then we plug everything together, because on this, we still have to add the expected sum of the payments to get the expected social welfare at equilibrium. And this is something that we'll formalize next time by introducing a notion of so-called smooth mechanisms. Until then, see you, have a great time, and stay safe.